Inference, I'm going to begin by reminding you earlier in the semester when we talked about linear regression. Recall the situation was that you had a numerical explanatory variable, which we always called x, and a numerical response variable called y, and we were interested in the relationship. We learned to make a scatter plot, which was a visual representation of the relationship. We learned to compute the coefficient of correlation, R, which measured the strength and the direction of a linear relationship. And we computed the least squares line. We wrote that y hat equals bx plus a, where y hat is the predicted value of y, or we will think of it now as the average value of all the y's, all the values of the y variable, when the x variable is equal to the particular value x. B, the slope, tells you the average amount you expect y to increase when x increases by 1, and A, the y-intercept, tells you the average y value when x is 0. Finally, we interpreted r squared as the percentage of variation in y that's explained by its linear relationship with x. So that's all what we learned about the relationship between two variables, but now we want to distinguish between the sample and the population. And in particular, we're going to, because all we have data about generally is the sample, we're going to look at the least squares line and r squared and things like that for the sample, and we're going to use it to predict what the least squares line and things like that should be for the population. First, we need a little terminology. When we're in a sample and we compute the least squares line and R, then R and A and B are statistics. They're summary about the sample. So we'll represent them by the Roman letters R, B, and A, as we have been doing. But if we imagine, we will rarely actually compute, but if we imagine the population coefficient of correlation, the slope, and the y-intercept for a population, those quantities are parameters. And following our convention, we will refer to them by Greek letters. We'll use rho, which is the ancestor of our r, although it looks more like a p, to stand for the coefficient of correlation, beta, which looks pretty much like b, which is its descendant, to represent the slope, and alpha, which more or less looks like an A, looks more like a fish swimming to the left, but we'll call it an A, it's the ancestor of A, to represent the y-intercept. Very important point is if x and y are independent. Remember, that means that knowing the value of x tells you nothing even probabilistically about y. If they're independent, that means the slope is 0. Well, for instance, when you increase x, you would expect nothing at all to happen to y, neither an increase nor a decrease. Since the slope is the average amount you expect y to increase, the slope is 0. On the other hand, if the slope is positive, then the variables are associated. In fact, they're positively associated. And if the slope is negative, they're negatively associated. So all that is to say, if you're interested in whether two variables are related, or whether they're positively or negatively correlated, more precisely, you can phrase that question as asking, is beta different from 0? That would be how you'd say they are associated, or is it greater than 0, positively associated, or less than 0, negatively associated? So that means the natural hypothesis test for linear regression is to take as our null hypothesis beta equals 0, and as our alternate hypothesis beta is less than 0, or greater than 0, or simply different from 0. That's natural because, as you perhaps have noticed, in all of the other procedures where we test a claim about association, where we look at the relationship between two variables, our null hypothesis is always that the variables are independent, and our alternate hypothesis is generally that they are associated, or sometimes we get more precise versions of associated that are analogous to positively and negatively correlated. We'll also give a confidence interval for beta. Beta is the most important description of the relationship between x and y, and the size of beta measures the size of the effect of x on y, assuming that x is causally affecting y. So the most important questions to ask are, is beta positive, negative, or zero, and how big is it? So that's what we will address. I should let you know that there are procedures to estimate alpha or do hypothesis testing about alpha, as well as about rho and rho squared. They're much less useful either because, for instance, alpha is not a very useful thing and doesn't say very much about the relationship, or in the case of rho or rho squared, the procedures don't tend to work very well and they don't give you a lot of information about what actually rho or rho squared probably is. So by far the most important procedure, the only ones we'll learn, are for estimating beta, which is the best description of the relationship. I'm going to give you a quick summary of how to do linear regression inference. We'll use a template, but you'll actually see it when I do an example. So I will go through this quickly. Of course, it starts by pasting your data into the Data tab of a template called the Simple Linear Regression Template. Notice our data now will be for each individual two numbers. So it will be two equal-sized columns of numbers. That's what you'll be pasting into the Data tab. And you'll remember that when we made scatter plots, we always had to put the explanatory variable first. That will continue to be important here. As you paste, you should pause for a second and make sure you have pasted the explanatory variable first, or all sorts of things will be incorrect. Next, as we did before, and I will remind you, you make a scatter plot of the data. Then we'll go to the Regression tab, where we'll read off things we've already learned how to compute, the least squares line, r squared, and other similar information. Then we'll go to the Model Inference tab, and we will enter a confidence level and read off the confidence interval. We'll report this as follows. The C confidence interval for the slope of the least squares line relating the explanatory variable and the response variable in the population is point estimate plus or minus margin of error. And then we'll select the appropriate alternate hypothesis. No choice about the null hypothesis, the usual 3 choices for the alternate hypothesis, and we'll report this data is or is not significant evidence at the alpha significance level that there is a correlation between the explanatory variable and the response variable in the population. That's what you'd say in the two-tailed alternative, beta is not 0. If you're saying beta is positive or negative, you'd report significant evidence that there is a positive or negative correlation between the two variables. So let's take a look at an example. The example we've seen before, the file exercise affects sleep, based on a group project that was done a few years ago. Convenience sample, you may remember, of adult Americans, asked each one how many minutes per day they exercise and how many minutes per day they sleep. We're interested in how exercise affects how much you sleep. We will use this data to test the claim there's a relationship between exercise and sleep at the 5% significance level, and we will give a 95% confidence interval for the slope. So let's go and do that together. On my website, we will first go to Data Files, and we will click on Exercise Affects Sleep, and I've already opened that up because I've been having such trouble with the speed of my computer during these. And we've got 2 variables, amount of exercise and amount of sleep. Exercise is the explanatory, because that's what we're thinking of as affecting sleep, and that's already first, so we can just copy these 2 columns. And then we go to the template page, and linear regression is below all the templates we've done under its own line, Simple Linear Regression. And we open that up again, and I've already set it up here. And we're going to paste. If you clicked on columns A and B, the whole columns, then just click on the column A and paste it in. You will be writing over data that labels explanatory and response variable. And notice there's a bunch of values here that fill themselves in. You might be able to guess what these things are. This predicted column is what the least squares line, which it's already figured out for you, predicts for y. So the x value of 60 corresponds to a y, a number of minutes of sleep of 444.65. This is just a repeat of the explanatory variable. You'll see why in a few minutes. And here are the residuals. Remember, the residual is the actual y value minus the predicted. So in this case, this first person slept 35 more minutes per day than you would have guessed just knowing how much they exercise. Okay, first thing to do is to make a scatter plot of your data. So highlight the two columns and click on Charts and Scatter Plot. The first kind of scatter plot. And here's our scatter plot. You can see a slightly negative relationship, but looks pretty weak, and it looks pretty linear, though it's got two outliers in the x direction, which perhaps are a small cause for concern. You might view that as a slight sign of curvature, but I would not. The first thing that we can do is all of the stuff we learned how to do in terms of drawing the trend line and writing the equation in r squared. All of that is worked out in the Regression tab. This tells you how many data points you have. It tells you the mean and standard deviation of x and y, which is useful, you know, for computing the slope in r. It tells you r. It tells you r squared. That's more important, so it's in bold. And it tells you the slope and the y-intercept. It puts it in this jazzy form here, where it says the name of the variable equals the slope times the explanatory variable plus the y-intercept. You can even enter a value of x here, and it will predict for you a value of y. That's all pretty and helpful. Remember the interpretations here. This is saying each additional minute of sleep, each additional minute of exercise that you get, on average, you expect to sleep about 0.46 minutes less. And if you didn't exercise at all, you would expect to sleep 472 minutes per night. But the new stuff happens in the Model Inference tab. Here's the confidence level. This is not a very pretty template. If we change the value, it changes the interval down here, point estimate plus or minus standard error. So remember those numbers. We'll bring them back over. And then our null hypothesis is always that the slope is equal to 0. We pick our three alternate hypotheses. Remember, we were testing the claim that there was a relationship with no presumed direction. So our p-value is 0.0727. With those numbers in hand, let's return. We report the 95% confidence interval for the slope of the least squares line relating exercise per night and sleep per night in adults is minus 0.466 plus or minus 0.510. I just want to point out that's a huge interval, right? It goes from minus 0.04 to almost 1. You will find that confidence intervals for the slope tend to be pretty broad, broader than you might expect, particularly in cases like this where there was a very weak association, right? R squared was 6%, so just over 6%. So 6% of the variation in sleep is explained by how much you exercise. Consequently, there's very little signal there to see in the noise. That's why there's such a broad confidence interval. And we tested the claim that there was a relationship, and we found a p-value of 0.0727 that is not quite significant at the 5% level. This data is not significant evidence at the 5% significance level that there is a correlation between exercise per night and sleep per night in adult Americans. If you think back to that scatter plot when you looked at it, you probably thought, yeah, there seems to be a negative relationship, but not a very strong one. And typically, if that's how you feel, like, I'm pretty sure I can see a negative relationship, you may or may not get significant evidence. If you look and it's blindingly obvious, you will get significant evidence. So that's all not too bad. You paste in your data, you choose your alternate hypothesis, you select your confidence interval, you read them off. The format in which you report them is pretty similar to the past, so none of that should feel very new. Unfortunately, the assumptions are a little more complicated. They're a little more complicated because linear regression is a much more involved procedure, and there are more theoretical assumptions involved. I'll remind you, all of our assumptions begin with a theoretical assumption. The population is infinite. The variable is exactly normal. And then that quickly gets replaced, and what we always spend our time on is a rule of thumb that's close enough. So we need to talk a little bit about what the theoretical assumption is, and then we'll talk about the rule of thumb. Recall that the residual of a data point is the difference between the actual and predicted y values. So y is the actual value minus bx plus a is the predicted value. That tells you how far off the point is from the underlying relationship. The fundamental assumption that makes the linear model go, and this is called the assumption of the linear model, is we assume that residuals of the population least squares line are normally distributed and are independent of x. Normally distributed, you know what that means. Independent of x means anywhere you look on the x-axis, as you sort of slide along the x-axis and look how the points are distributed above and below the line, it doesn't vary. They're as likely to be above as below. They don't get more or less spread out. They remain a constant shape in how they're scattered around the line. That assumption is about what happens in the population, which of course we have no direct access to. So our rules of thumb have to take what happens in the sample as a stand-in. The first rule of thumb is what we see in the sample is not going to be any kind of indication of the population unless n is fairly big. So unlike the other procedures where there was at least where we would willing sometimes to assume the variable itself was normal and then we didn't need n to be big at all, here we're not going to even attempt that. It does not make sense to do linear regression unless you have a sample size of at least 40. Under that circumstance, the notion that it should be independent is gotten by looking, and I will show you how to do this, at the scatter plot of residuals. So here we're relating the x variable to the variable, the residual. Residual is a random variable. Each individual in the population has a residual for this least squares line. So it's a variable, a numerical variable. We're going to look at the scatter plot to see that it looks independent. We'll do that. I'll show you how to make that scatter plot. And then to see that the residuals are, we don't need them to be actually normal, as the assumption is. It's enough if they're reasonably symmetric and without outliers. And that is built into the residuals tab. So I will show you how to do this when we get to it. Let me just summarize what all the assumptions are. We still have the simple random sample assumption. There's always one sample in linear regression, so it's very simple. And we still have the large population assumption. Again, one sample, one population. That's totally straightforward, but instead of the normality assumption, we have the assumptions of the linear model, which have three parts. We need n to be at least 40, we need the scatter plot of the residuals to be even, and we need the histogram of the residuals to be symmetric. So let's do this for the exercise sleep example. Simple random sample, not met. We said it was a convenient sample, if you recall. Large population. Our sample size was 50, so that means we would need there to be more than 1,000 adult Americans. No problem. The linear model. First, we need n to be at least 40. That's fine. N is 50. Next, we need the residuals of the scatter plot to be even, and the residual histogram to be symmetric. So we're going to take a look at that. The first one we look at in the Data tab. We have the explanatory variable here, and we have the residuals here. And now, because these are calculated quantities, unfortunately, you cannot simply highlight the two columns and click on scatterplot, because you get a blank scatterplot. Sorry. Instead, you have to do this slightly annoying thing, which is you have to highlight not the two columns, but the array of data. So starting in the upper left-hand corner and going to the lower right corner of those two columns, D and E. And now if you click on scatterplot, you get a lovely looking scatterplot. This looks like the previous scatterplot flattened. You take out the linear relationship and only the scattering around the line is left. That tends to accentuate problems, which is good because that's what we're looking for. If there was a curved relationship, this would also be curved. In fact, it would tend to look much more curved, and that would be a sign that the variables are not independent. As you vary x, the values of the residuals vary in the y direction. Here, this looks quite good. As you vary x, you see a pretty uniform distribution in the y direction until you get out here where there's a couple of outliers. If there's only 2 points, you can't expect them to have any kind of standard distribution. So we're not too worried about these two outliers, and overall I would say that this is the y variable scattered evenly in the x direction. The other assumption, we click on the residuals tab to check out. Here is a a histogram of the residuals. This histogram is slightly skewed, but not a problem. It needs to be pretty heavily skewed to be a problem for this assumption, precisely because n is large enough that it handles a lot of such issues. So this also meets the histogram assumption. So let's return. So we said that the residual scatter plot was reasonably even, though the outliers in x are a caution, and the residual histogram was reasonably symmetric, slightly left skewed. So the linear model assumption is met. Let's do another example. Another group project asked every fourth student at Barone Dining Hall how many nights they went out drinking and how many classes they skipped per week to see if drinking increased how many classes you skip. So we're going to test at the 5% significance level whether there is a positive correlation. So this time we're adding the word positive, so we use a one-tailed test. Positive correlation between drinking and skipping classes at Fairfield U students, and we're going to give a 95% confidence interval for the slope. The data is at the data page of my website. In the interest of time, I'm going to go straight to Excel where I've already entered that data in. And that is here. Here is, nights, weeks spent drinking and classes skipped. Here is the scatter plot. I plotted here for you the predicted values. You can see that it is a clear positive association. Perhaps you see a little bit of a sign of curvature. It's not quite clear. We'll address that later. I'm going to skip straight to the model inference page. Our 95% confidence interval was 0.7272 plus or minus 0.2058, and we're testing for evidence of a positive slope, so our p-value is 7.2 times 10 to the negative 11th. So let's return. P-value, 7 times 10 to the negative 11th. So this data is significant at the 5% level that nights spent drinking is positively correlated with number of skipped classes in Fairfield U students. If you go out drinking more, on average, you will skip more classes. The 95% confidence interval for the slope of the least squares line relating nights spent drinking to number of skipped classes at Fairfield U students is 0.727 plus or minus 0.206. This was a much stronger association, and you can see that the confidence interval is a bit narrower. It only goes from 0.5 to about 0.9 something, but it's still not all that narrow. it's hard to do do inference with linear regression unless you have a lot of data. So for each additional night of drinking, you can expect on average to skip an additional 0.5 to 0.9 classes per week. Let's check the assumption. Simple random sample, it is not met. It's a convenience sample. For example, one possibility of sampling bias is, depending on what time of day, which they did not say, they sampled people at Broome, they could be favoring night owls or early risers, which might relate to both those variables. Large population assumption. N is 127. We'd need at least 2,540 Fairfield U students, and that's surely met. Linear model. N certainly more than 40. We have N equals 127. The scatter plot of the residuals is not met. Let's go back and look at that. On the data tab, I already made the scatter plot of the residuals, and you can see that little hint that you may not have recognized here of curvature is much more pronounced here. You can also see that as x increases, the data tends to get more spread out. That's a smaller problem, but still indicates that the residuals and x are not independent. So here, this is enough curvature, I would say, to be a cause of serious concern, so I would be inclined to say that this assumption was not met. You may have noticed checking the assumptions for linear regression is a little bit more art than science. It's more of a judgment call than things we've done in the past. And, oh, I'm sorry, I didn't mean to go back because I wanted to check out the histogram of the residuals. This is bimodal perhaps, but it is not very skewed. So I would call that pretty symmetric. So this assumption, the histogram of the residuals being symmetric, is met. I want to pause here because because it's a group project and you're all thinking about your group projects now. Among the things you have to do with your group project is identify sources of sampling bias, measurement bias, and lurking variables. Let's do that here. One's pretty straightforward sampling bias is that heavy drinkers and frequent class skippers might be less likely to show up at meals than other people. So you're leaving out the extremes of both variables in this case. There are a number of possible sampling biases which depend on what time they sampled, and this group project didn't tell me what time they sampled, so they left out information that you would need to assess the possible sampling biases. So that's a mistake in terms of the study. You want to give enough information about the sampling process that people can decide what are the potential sampling biases. For example, if they sampled during popular class times, they might have favored class skippers. If they sampled during regular meal times, they might favor people with regular habits who you would guess would drink and skip less. Measurement bias is actually pretty straightforward. It is safe to guess that people might underestimate both their drinking and their class skipping out of embarrassment. On the other hand, it's also plausible that people who are hanging out with their friends at Broome might exaggerate how much they drink as a kind of showing off. Both are plausible. Both may very well be in effect. Who knows which one is stronger? Lurking variables. Here's one. Athletes. That's a group of people who are likely to drink less, so that affects the explanatory variable, and they may perhaps skip classes more because they have practice and because they lose sleep over practice and things like that. Of course, the most straightforward one is rule-abiding students, good students, well-behaved students, however you want to say it, are less likely to skip class and less likely to drink. That's an aspect of the student which affects both variables. Likewise, students more concerned about their grades will skip less and drink less. And there are lots of others. Okay, there's so many key points here, it takes up 2 pages. After watching this lecture, here's what you should be able to do. State the null and alternate hypotheses for linear regression. You should be able to enter your 2 columns of data in the data tab of the template. You should be able to make a scatter plot and read off the basic linear regression information in the Regression tab. You should be able to select an alternate hypothesis and read off the p-value in the Model Inference tab. Using that, you should conclude and express your conclusion in a sentence of the form, this data is or is not significant evidence at the alpha significance level that the explanatory variable is positively, negatively, or simply correlated with the response variable in the population. And you should be able to select a confidence level and read off the confidence level from the Model Inference tab and express the confidence interval in a sentence of the form, the C confidence interval for the slope of the least squares line relating explanatory variable and response variable in the population is point estimate plus or minus margin of error. And finally, oops, there's a little typo there, only the second line is relevant. After processing this lecture, you should be able to check the first two assumptions and all three parts of the last assumption of the linear model, including making and assessing a residual scatter plot and assessing the residual histogram.